Good morning.
Morning, sir.
Morning. So, welcome back to another session on image processing. Uh, Actually, the last class, I thought there is a regular class, and just to avoid missing the topic, so I had recorded and had sent. And actually, 38 of you have solved the problem and replied to in fact, uploaded your answer. Uh, I don't know what happened to the other students. So there are 38 responses that I could see so far, which means uh, others are not have not done it. So I'm closing the I close accepting the responses because by this time it should have been done. So others will be losing the marks that was allotted to this. I just want to open out one, in fact, response because that is almost correct, except a small mistake. So, others, you just evaluate yourself where you have gone wrong or whether it is correct. Okay. So, let me share my screen. Okay. So, I'll just take one of them. I think it is Purnima. I have just verified one or two. So, I'm sure others also would have done it correctly. Is this uh, scanned document of Purnima visible to you?
Yes, it's visible.
Okay. Okay. So in histogram specification, you will be given the input gray level. In fact, the range of gray levels. So this is a 3-bit image, so you can have maximum 8 gray levels starting from 0 to 7. Probability distribution of the input gray level is also given. This is one of the way of asking the problem. Otherwise, you can be given the image itself where this calculation should be done by you. I hope you remember what we discussed in the previous class. And other thing that would be given in histogram specification is the target histogram. So this is the input histogram and this is the target histogram. So I want you to modify the image which has histogram of this nature to another image which has got histogram of this nature. So observe the table. This is not required. Since this was done in the class, I think she has done it. This normalized gray level calculation is not required, so you don't need to worry about this. So RK is given, PR of RK is given. So the steps all of you remember if you have listened to the video, you have to uh, perform histogram equalization of the input histogram, input PDF. So zero point 0.6 is copied as it is. Then zero point 0.2 plus zero point 0.6 is 0.8, 0.8 plus 0.15 is 0.95, 0.05 plus 0.95 is 1. This is one step. Second step is given the target histogram, equalize that also. So you can observe that 0 is 0, 0 plus 0 is 0, 0 plus 0 is 0, zero point 0.1 plus 0 is 0.1, 0.3, 0.6, 1. Now once this is done, now you have to start mapping. Start from the input gray level 0. Just see after equalizing where is it falling. It is 0.6. Now try to identify a value in the equalized histogram of the target which is equal to zero point 0.6. Same value or close to this. So you can see that zero point 0.6 is there. Now this 0 point 0.6 has come from 6. So which means all zeros should be mapped as 6. So first step what she has done is correct. Then let us go to 1. 1 is the equalized histogram is 0.8. Now I have to locate 0.8 in this. Now observe here 0.8 is not there. The closer value either I can take 0.6 or I can take 1 because the difference is 0.2 in both the cases. So in this case she has taken it as 0.6. Okay. So since it is taken, it is close to 0.6. Uh, the value which it has come from 6, so she has copied 1 to 6. But some of you have copied 1 to 7, that is also correct, because 7 is actually the CDF value is 1. So zero point 0.8 is, I can also take it to be closer to 1, because the difference is zero point 0.2 in both the cases. So either you take this or you take this, the answer is correct. So he has done it like this. Others have taken this as 7. That is also correct. So if this is mapped as 7, that is correct. Now second 2 is 0.95. 0.95 is very close to 1, which has come from 7. So 2 is mapped as 7. Similarly 3 is 1. 1 is close to 1, so which is 7. So I think this is how this in fact the new gray level can be mapped. So which means all zeros should be copied as 6, all 1 should be copied as 6, and all 2, 3, 4, 5, 6, 7 should be copied as 7. This is the problem. Now, the problem is not complete. You are asked to plot the histogram. So, this is the input histogram, zero point 0.6, 0.2, 0.5, 0.05. This is the target histogram, 0.1, 0.2, 0.31. Okay. So on the x-axis, please don't show like 1 by 7, 3 by 7, 5 by 7. This is RK, the gray level, so it should be 1, 2, 3, 4, 5, 6, 7. So I think here show normalized gray level, but better to show the actual gray level. This is okay. I think in some of the sheets I have seen that this is written wrongly. What they have done is they have actually plotted this. That means probability of 4 as 0.1, probability of 5 as 0.3, probability of 6 as this is wrong. You should plot the probability. These are the CDF values. So please carefully observe. This is correct. What she has done is correct. I'm not telling others have gone wrong. I have just only randomly took her sheet and I have verified. So this is only for you to correct yourself, because I don't want to look at all of the responses. Now here I think is Purnima there?
Yes, sir.
Okay. See, you have plotted this as 0.6. I think what we have done is you have mapped both 0 and 1 as 6, correct?
Yes, sir. In the table, I missed that.
Okay.
Actually, we mapped 0.8 also to 1.
Okay,
But
okay. So if you had, so in the table, if you modify this as 7, what you have written here is correct.
yes, sir. In the table
Okay.
only I have to write.
Okay, yeah, yeah.
Sir.
So I hope you understood. Otherwise, I think so you read this as 7 here, because that is also okay. 0.8 is close to 1. So if this is read as 7, all of you observe all zeros are modified as 6, which means probability of 6 in the output image is equal to probability of 0 in the input image. Probability of 0 is 0.6. That's what she has written here. Probability of 0 is probability of 6, so that is 0.6. Probability of 7, in fact probability of 7, because all values from 1 to 7, they are all mapped as 7, including this should be corrected. So all these probabilities should be added. So zero point 0.2 plus 0.15 plus 0.05 and all other values. So that's what she has done. All these values are added. So it's equal to 0.4. Okay. So this is the problem. Those of you who could complete it, very good. I think there are some mistakes. I think probably after me explaining it, you now know where is the mistake. Please correct it. I'll not go to each and every response. Just to save time, I took only one example. Okay. So can we move on to the topic? Any doubt? Anybody who want to who have any
Yes,
doubt? Okay. And before I start the new topic, I think let me remind you. Afternoon we have a session by by Dr. Praful, who is from MathWorks, and he is actually an expert in image processing. As you could, in fact, I have sent the uh, link also just now. Uh, so these are the topics that is going to cover. Very interesting topics. I definitely would like all of you to, of course, compulsorily you have to join. That is a different thing. But my uh, sincere advice to all of you is please listen and have an interactive session, because he has some discussions and projects. So this would be helpful to you to pick up your final year projects also. And lot of in fact topics he is trying to cover. Of course, he said he will not be going to the finer details of the algorithm. He want you to learn how to build apps by using MATLAB. So uh, at 2:30 sharp, join through this link, and during the session please keep okay, maintain discipline. After the session I want you to interact. Okay, so let us make use of this very good presentation. In fact, if everything goes well, if offline classes are started, he has agreed to come down to the institution and give a presentation and interact with you more on many applications. Okay, so he did his PhD from IIT Kharagpur. More about him we will be telling you in the afternoon. So all of you join without fail and uh, interact with him in the end and try to clarify your doubts. This will be a very useful session. Okay. So with this, let us now move on to the next topic. So the next topic is actually what is known as spatial filtering. So this is again enhancement in spatial domain. The difference is, if you remember, in fact, for example, if you take out this example itself, what we did is we went to each and every pixel, looked at the gray level, and saw where it is falling, and copied each gray level to a new gray level. In fact, the problem that I explained just now did this. So you are doing what is known as point processing. So all your previous techniques that we discussed, all the techniques like starting from image negative, logarithmic transformation, power law transformation, histogram, contrast stretching, all of them, they actually do what is known as point processing. That means every pixel in the input gray level is modified based on some transformation function. Now what we discuss from here onwards is again in the spatial domain, but we use what is known as a mask or a template which will run. That means this is actually a neighborhood processing technique. That means we will we will take a small neighborhood and take a decision based on the values of the pixels in this neighborhood and also the weights of the in fact the entries in this mask or kernel. Okay, so as you could see here, there is this is the image. So this kernel, in this case, it is taken as 3 cross 3. Will start from this corner, move up to this corner, come back here and continue. So it just does a raster scan and reaches this corner in the end. So what is the principle? The principle is this. So as I said, this kernel will move from one pixel to other pixel and take a decision. And this kernel will have some weights in it. Okay. So let us just take those weights as 0, 0, -1, -1, -1, 0, etc. There are some weights. There are some numbers, that's all. So you'll have some numbers here. So when the pixel, when the kernel is on maybe this portion of the image, let us see. Okay. So what it does is it multiplies w00 with f of x comma y and adds with w -1 with f of x. That means the weight is multiplied with the pixel value here. So the weight here is multiplied with the pixel value here, and whatever result you get, that result will be replacing the center pixel. So this is how the spatial domain operation takes place. I have some weight, you multiply that weight with the original pixel value at that location, do it for all the 9 pixels, and then whatever value you get, replace the center pixel by that. Okay, so we will take an example to illustrate this. So there are two different spatial filters that we are going to discuss. All of you know, the moment we say filters, the first thing that comes to your mind is a low pass filter. So as you know, low pass filter is the one which passes the low frequency components and attenuates the high frequency components. So in an image, high frequency components means edges. So if I say a low pass filter, edges are blurred or smoothened, That is why we also call a low pass filter in image processing as a smoothing spatial filter. Okay, so smoothing spatial filter means it's a low pass filter that I'm going to use. And since it is smearing edges or smoothing edges, actually it performs blurring. Now this blurring is required. Those of you who have completed the course on MATLAB image processing using MATLAB and also the on-ramp course, you know this is one of the pre-processing technique that when we are doing segmentation. For example, if you have some small maybe artifacts in the image, before we do segmentation, we first smooth it by a filter so that this artifacts will be removed and the segmentation will give you accurate results. Okay. So normally this is used for blurring, but blurring has an advantage, even though it has a disadvantage that edges are blurred. It has an advantage that the noise is smoothed because blurring means it is smoothing, so the noise gets smoothed. Now, as I said, it is used for pre-processing. In fact, I have already explained this. Removal of small details prior to an object extraction. So when I am doing segmentation to extract some object, there could be some small details which are not part of this object. So what we do is before you perform segmentation, you just smooth it so that the small details will be missing. Then you perform extraction. And also it is used for bridging some small gaps in lines or curves. Okay, so this I will be explaining you in the frequency domain representation. So for now, let us just remember that this is another use of blurring. Okay, whenever, for example, when I am doing character recognition, it's quite possible that the characters are not completely connected. There could be some missing gap, there could be some gap. So this gap can be filled by using simple low pass filter. Okay, more about it we'll discuss in frequency domain with filtering. Now these are the two prominent low pass filters that are used here. So this is a 3x3 filter. As you could see, all the values are multiplied with 1 by 9. That's why 1 by 9 is taken out. So this is 1 by 9. All these values are 1 by 9. And we call this as a box filter because you know all the value weights are 1. So if you just look at it as a three-dimensional structure, this looks like a box. Okay. So that is why it is called a box filter. So all the weights are constant here. The difference here is the central one is weighed more as compared to the other one. Okay, so this is called a weighted average filter. This is a box filter. So in a weighted average filter, the central pixel is given more weightage as compared to other pixels, whereas in a box filter all the pixels are given the same weightage. Okay, so this is a equal weightage filter or a simple averaging filter, but this is a weighted average filter. In fact, both of them are low pass filters. Observe one more thing. If you add all these weights, you will get it as 1. If I add all these weights, you will get it as 1. Because, for example, 1 by 9 added 9 times, you will get it as 1. This also you can do it. For example, add all of them. 4 plus 8 is 12 plus 2, 4 is 16. 16 by 16 is 1. So this is one observation of a low pass filter. Okay, when you add the weights, the weight will be equal to the sum of the weight is equal to 1. What does it mean? Suppose if I have a smooth region, then low pass filter does nothing because a smooth region means it's a low frequency component. It is just allowed as it is. That is the reason why the sum of weight should be equal to 1. Now let us take an example now to illustrate how this could be helpful to us in smoothing the image and maybe. So we will just go to the OneNote. Is the OneNote visible? Can somebody respond? Is it visible?
Yes, sir.
Yes.
Okay, so I'll just take an image, a small image I'll take just for the sake of explaining it. So let me just take a 4x4 image. and intentionally I'll take some specific values. Okay, so I'll take 4x4 image. The pixel values are 10, 10, 100, 100. So this is the image. Now let me just use a averaging filter 1 by 9 into this. So this is a simple box filter. So I want to apply this here. So what you are supposed to do actually is this. You have to bring it. In fact, you have to bring this center to this point. So let me just show it in red color just for the sake of okay. So separating them. Now the weights is this is 1 by 9. So I'll have 1 here. What I am writing in red color is actually your kernel. What I have written in black color is the original image. I hope you can visualize what I have tried doing it. Okay, so don't read this as 110. This is that 1 is the weight of your kernel. So you have to multiply all of them and replace the central pixel by that. So what would be the output? Can somebody tell me? What would be this value? So as you could see, okay, so if there are no pixel, then which means you can treat it to be 0. That is one of the simplest way of applying the filter. There is another way where we will actually replicate the border and then do it. But let us not go to such a detail. We will assume all these values are 0. That means those which are actually in the border here, these values are 0. So it will be 10 into 1 plus 10 into 1 plus 10 into 1 plus 10 into 1. So it will be 40 divided by 9. So this value will be 40 divided by 9. Did you understand? Is this understood how
Yes.
I got this? Okay. Now if I go if I move this by 1 pixel, okay. So I think now you can calculate by mind and tell me what would be this value. I'll move this kernel by 1 pixel to the right. So it will be 100 plus 100, 240 by 9. Is that correct?
Yes.
Correct. Now if you move it still further, it will be 420 divided by 9. Correct. So I hope you are visualizing. I'm just trying to move this pixel by pixel to the right. So for how 420, because 100 plus 100 plus 100 plus 100, 400 plus this. So 420 divided by 9. Now if I still move it further, what will I get? That means when the kernel is here, it is 400 divided by 9. Okay. Now let us neglect the rest of the things. Now if I just move the pixel kernel here, okay. So can somebody now quickly calculate how is this value calculated? What is this value? I hope you know what is the procedure. So the center pixel should be here
60
now.
by 9.
Yeah, 60 by 9. Very
60
good.
by 9.
Yeah, this is 60 by 9. Now what is this value? 360, correct? 300
Yes, sir.
plus 10 plus 10 plus 10. Okay, 360 by 9. If I move this side here, so it is 630 by 9. If I'm making any mistake, please correct me. Then if I further move to the right, it is 600 by 9. Okay, then what are the other values? So if I'm here, 60 by 9, and if I move here, 360, correct? So I further move,
Yes, sir.
okay, it is 630 by 9. Anyway, this can be verified by using MATLAB. So before that, let us just try to do it manually. So what would be this pixel? 600 by 9. Now when I come here, it is 40 by 9, and this will be 240 by 9, and this will be 420 by 9, and this will be 400 by 9. Okay, so this will be your image now. Okay, now let me just quickly, one of you should give me these values. What is 40 by 9?
4.44.
4.44, so I'll just approximate it as 4 because gray level should be integer. 240 by 9,
26.6.
then I'll call it, I'll make it as 27. 420 by 9,
46.6.
46. Okay, 400 by 9,
44.4.
okay, I'll just make it as 44. I am approximating it to the nearest. Okay, can you quickly tell me the other values? 60 by 9,
6.66.
then I'll make it as 7. This is 40, I think.
40.
Yeah,
75.5.
I'll make it as 76 then.
66.6.
Okay, so 60 by
6.6.
9 is 7, 40, 76, 67. This is 4, 27, 46, 44. I am assuming that the steps are understood. Okay. Now, for example, if these, suppose if the image has got 100 here also, let us assume that if it has got 100 here, what would be the output values? Can somebody tell me what would be these values? These values. Suppose if it is a 4x5 image where the other pixels are 100. Hello? Am I audible?
Yes, sir.
Yeah, so suppose if I in fact center the pixel here, the kernel here, all added up is 900. 900 divided by 9 is 100, correct? So this would have been 100, this would have been 100, and of course other values depends on okay, so okay, whatever it is. Now carefully observe. Suppose if the image is smooth, I am getting the same pixel value in the output. And now notice this. What you should notice is, notice this. There is a change from 10 to 100. So I had a pixel value equal to 10. It has changed to 100. So this is actually an edge in an image. Please observe this. So there is a change from 10 to 100. And observe that in the output image what has happened. Okay. What would you expect? What has happened? Can somebody tell me? This is the edge. Okay. So whenever it is 10 here, it would have been 10, but later you can see it became 4. Then it, in fact, I'll take this. It became 7. Then it became 40. Then it became 76. Then it became 6. Okay. Of course, since it is a border, it has become 67. Otherwise, what it would have happened is something like this. Okay. Did you notice that? Any comment
Yes.
on this? Nobody want to comment?
So in first graph, sir, there is a sudden change. The
Yeah, correct,
intensity
correct.
of
So
the
there is a sudden transition. So this is a sharp edge in the image. So if I apply this type of filter, which is a box filter, which is also called smoothing filter, the edges get smeared or it is smoothened out. Correct. So that is actually the observation. So when I use this type of filter on an image, any edge information will get smoothened out. In fact, if I had taken a bigger image, it would have been better. So let me just demonstrate this using MATLAB so that it would be still easier for you to understand. Please wait. So, I'll just take an image, say x equal to the same image I'll take, but I'll probably take a bigger image. So I'll actually take an 8x8 image. This is the first row. I'll copy this more number of times as a second row, third row, fourth row, fifth row. So maybe so this is an image. Okay. So same image, but only thing is that it just taken more number of pixels. You are able to see the image now. It's just a I think it is 5x8. Is this visible? Hello.
yes, sir.
Okay. Now I'll take a filter which is equal to 1 by 9 into, actually there are many ways of generating it, so I'll just use this method. There is another way of generating it. So this is your simple 3x3 box filter. Okay, ones of 3 comma 3 will generate all ones, and I am multiplying all of them by 1 by 9. Okay, now to apply this filter, the operation is just a simple convolution operation. So I'll just say convolution 2, because it's a two-dimensional convolution x with h, but I have to restrict the size of the image same as the input. Therefore you have to use what is known as same. Okay, hope this command is visible. Now I have applied the filter. Neglect the border, because border is always a problem. Even in our problem also we have seen the border values are taking, because obviously when you go to the border, some pixels are missing here. Therefore I cannot expect the value so that is why usually in an image normally the borders are neglected. So if you neglect the border, if that means these values are neglected, don't worry about it. Look at only this portion of the image. Okay, look at only this portion. Observe, there is a transition from 10 to 100. Okay, which is a sudden edge. Now observe here, from 10 it has gone to 40, from 40 it has gone to 70, and from 70 it has gone to 100. So this is exactly what I was explaining here. It was taking a transition from 10 to 100, but because of the low pass filter, the transition is going from 10 to 40, 40 to 70, and then 70 to 100. So this is actually the effect of smoothing. That means any edge like this gets smoothened. So I think you can also probably do this on an image. Let me just check whether I have some demo directly available. Yeah, so I'll just run this, explain the code later. Let me just first run and see the results. Yeah, so one by one I'll show the image. So this is the original child image. Is the image visible to you?
Yes, sir.
Okay. This is after I applied a 3x3 kernel. Now the next one is after I apply a 5x5 kernel. The next one is after I apply a 7x7 kernel. So what do you notice? So this is 3x3. Maybe I can just put them together like this. And this is 5x5. Let me just show some portion of it. Then this is 7x7 filter. So what do you notice from this to this? The original is here. This is the original. This is the original. So what is the observation? Look at the text portion particularly. Even other portion also you can easily observe. So as you can see, look at the text portion. The text portion is smeared. In fact, here also you could see that the eyes are very sharp here, whereas here it is blurred, and it is still blurred here. So this is a low pass filter. Okay. So let me now explain the code. I have just read the image, converted into gray because the operation that I am applying is for gray. So RGB to gray is the command. This is what I told you. So F special is the command which generates a filter. If I give average here, it will generate a simple box filter of this dimension. So this is 3x3 and then I am doing convolution, and as I said, to keep the image size same after the output, I am just using this command same and then displaying it. Similarly, an average filter of 5x5 applied, an average filter of 7x7 applied. Okay. So what you should notice here is whenever I apply this type of filter, the image gets in fact smeared or blurred. And the advantage in the second case is since the center pixel is weighed more compared to the other pixels, in this case there is no doubt smoothing, but even the edges are also kept intact. That means there is a less blurring of edges in this case as compared to this. So the smoothing effect is less in this case when compared to this. See, whenever you are trying to smoothen noise, if I use the second type of filter, no doubt the noise gets smoothened, but at the same time edges will also be preserved. So this is a better filter compared to this. Okay. So let us see the results. Is this image visible to you?
Yes, sir.
Okay. So this is actually a typical example that is taken just to demonstrate the application of a smoothing spatial filter. If you carefully look at this, there are some alphabets of different font size. There are some squares here which are actually noisy squares. If you just observe, they are all textures. So this is just to see how the noise gets eliminated. Okay, just to see the effect of smoothing filter on noise. And there are some square dots here of different size, and there are some lines here which are kept at a specific distance. So all these details is available here. So it is a 500 cross 500 image, and you are trying to apply a filter mask of size 3 cross 3, 5 cross 5, 9 cross 9, 15 cross 15, and 35 cross 35. These are the results of all these filters. About the image, the black squares at the top are sizes. Okay, so these squares of size 3, 5, 9, 15, etc., etc., and they are separated 25 pixels apart. That means from one square dot or square to other square, the difference is 25 pixels. The letters at the bottom, okay, are of the font size from 10 to 24. That means 10, maybe 12, 14, 16, 18, 20, 22, 24. These are the different font sizes. Okay. Now, if you observe, obviously when I go to the higher dimension filter, that means 35 cross 35 filter, the smoothing is very high. So the edges are smeared. You can see that I cannot recognize that these are alphabets. I don't think I can recognize that there is a A here. But what you should notice is, if you observe this portion, which was the noisy portion here, the noise is completely removed. Do you notice that? So definitely smoothing filters are very good at smoothing the noise, but at the cost of smoothing the edges also. So whenever I am using such type of filter, I cannot simply take a very bigger dimension filter and try to smooth the noise, but because that will also spoil the edges. I should be very careful in choosing the size of the filter. That's what it demonstrates. In fact, it is well demonstrated with another example. Now observe that there is an image of this. This is actually a Hubble Space Telescopic image. Okay. There are some interesting objects which are to be now recognized. That means I need to segment these things. Now suppose if I directly give this to a simple thresholding technique and segment it. That means anything above this value it is white and below that it is black. What would have happened is all these small dots also that you see, which is a noise-like structure, will also be getting converted or getting detected. But I am not interested in those. I am only interested in these bigger ones. So the smaller ones I am not interested in. So in such cases, what they do is they'll apply a filter on this. So in fact, in this case, they have applied a 15 cross 15 averaging mask. So all these small dots are smeared, as you could see. Now if I apply a simple thresholding technique, only these bigger blocks or bigger objects are identified or detected. Okay, this is the example of why smoothing is important. Why should I blur before I do segmentation? Okay, in fact, this as a part of the core, the MATLAB course that you are doing, definitely you have this type of implementation that you have done there, applying a filter before doing segmentation. Okay, so this is about how you can use smoothing filter. Um, Another good example of a spatial filter is what is known as an order statistics filter. Order statistics filter, as the name itself says, it is actually arranging the pixels in an order and use some statistical measure to take a decision. In this case, in the previous case, what it was doing is it was not looking at the in fact, it was not doing any arrangement or ordering them. It just took each pixel value and multiplied with 1 by 9. Whereas here, what it will do is it will arrange the pixels in an order and then use some statistics. That means it will use some statistical measure, mean, median, max of the value, min of the value. They are all statistics that we are going to use. So depending on what statistics we use, we have different types of filters. Okay. So since I am just ordering and using some statistics, this is definitely a non-linear filter, whereas this is a linear filter. Okay, you just take some average, weighted average here, whereas here you use some order. So therefore, this is a non-linear filter. And as I mentioned, the response of the filter is based on the ordering. Okay, so you just put them in an order and then take a pixel. Then replace the center pixel by the resulting value. Okay, for example, let us take the median. I'll again explain this with some simple typical example. Okay, so I'll just take maybe first we will just take one dimension. Let us assume that I have some values like 10, 20, 5, 4, 2. Now if I want to apply some median filter on this, what they will first do is this should be order. Okay, so just put it in the increasing order 2, 4, 5, 10, 20. So you should first order it. Then take the median, and you know median is when once I order it, the median is the middle of the value. So 5 is the value. So I have to replace the center pixel by 5. Of course, in this case, the center pixel value is 5 itself, so it is replaced as it is. Okay. So now if I do it for an image, let me just take an image. I'll just take typically some values. Intentionally, I'm just taking these values. I'll take this as 0. Assume that I have an image like this. Now I'll use a median filter of size 3 cross 3. A median filter 3 cross 3. What I want you to do is don't go to the border pixels, because you know border pixels will always have problem, because I don't have these values to take any decision. So don't worry about the border pixels. Let us just try to do it for only this. The border we will neglect. Okay. So neglecting the border. So what you can probably do is you can just uh, retain the same values what you have in the border. That is the easiest way of doing it. So I'll just neglect these border pixels. I'll not worry about it. Now can you tell me if I go to this pixel, okay, that means if this is the center pixel, what are all the values? 9 values are there. So you have to put them in an order. So can you just tell me that order now? I am here. Okay, if you want using a different color, I'll show you. This is the current position now. So now put them in an order. 0, 10. Can somebody speak? 10, 12. All the 9 values, put them in an increasing order. That's all you have to do. 12, 13, 14, 15, 255. Is this correct? All the 9 values are come? Yes. That means these values, whatever I have ticked in green color, 9 values are there. Order them in an increasing order. Is this correct? Any doubt how I got this? Can somebody respond? Is my voice audible? Is there any issue? Hello?
Yes, sir. Yes, sir.
So voice is audible, right?
Yes.
Okay.
Yes, sir.
Okay.
Not good.
So is this understood what I have written in green color, how to apply the filter to this pixel? So I have just arranged them in an increasing order. I have to take the median. You know the median is the middle one here. So this is the median. So the center pixel here should be replaced by 12. Of course, it was earlier also 12, so there is no issue. Now let us move the filter. Now I'll use a different color. So the filter is here now. Somewhere here now. Oh, sorry, here. This is the filter now. this. Okay, I'll just put it in bigger box here. So now can you tell me the pixels in an order? So 0, there is a 10, 12, 14, 14, what else? 15, 15, 255. So the median of that is 14. So this value will be 14. And now I'll just take the box here. So this is the box now. This box. So you have to mentally okay, look at where we are. So I'll just write them. So this box, what are the values? I'm just arranging them in an order. So 0, then I have 11, 12, 12, 12, 12, 0, 11, 12, 12, 12. How many 12s are there? 4 12s are there. Okay. Then 13. One of you should speak at least.
Sir, 13.
Pardon? Is this correct? What I have written now?
Yes, sir.
Yes, sir.
Okay. So the median is this. So it is 12. This value will be 12. So you can even do the next one. I'll not do it. I want you to just find out what would be this value because the procedure is understood. But carefully observe what it has done. Earlier there was a 255 here. If you compare to the neighboring pixels here, 255 is a very large value. If you are comparing to a neighboring pixels here, 0 is a very small value because these are all 12, 13 and all, whereas this value is 0. So a 0 which is a very small value, a 255 which is a very large value, as you can see it is removed here. Okay, so 255 is replaced by 14, 0 is replaced by 12. Okay, so notice this, in an image a 0 means dark, a 255 means white. So this is actually called a salt and pepper type of noise. Okay, so that's what I just want to introduce here. Called salt and pepper type of noise. And the meaning is the name is given because you know salt is white color and pepper is black color. So any black dot on an image is a pepper noise, any white dot on an image is a salt noise. So both of them together, it's called salt and pepper type of noise. So whenever an image is corrupted by this type of noise, salt and pepper type of noise, we use a median filter. That's what I just want to demonstrate here. Okay, so median of the gray level replaces the center pixel. We have done that, and it is popular for impulse noise. In fact, impulse noise means a value going very high, so which is actually the salt and pepper noise, as I have already told. And of course the blurring is less here compared to linear filter. Okay, so this is exactly what we meant by order statistics filter. So max and min filter, I think procedure is same, but we will take it up in the next class. Let me just show you the results. So do you notice white and black dot on this image? If you want, I can zoom it up. Sorry. Just observe this image, this portion. You can definitely see white dot and black dot. Okay, there are some white pixels and black pixels. So when I have salt and pepper type of noise, if I use a simple averaging filter that you did in the previous discussion, averaging filter, it would have spoiled the image like this. Because you know, salt and pepper type of noise is an impulse noise. A smoothing filter actually smears it, smoothens it. That means a dot will just smeared around. Whereas observe this image, do you notice most of this noise is removed? Okay, so that is the advantage when I use median filter. So whenever there is an impulse noise, be very careful. Whenever there is an impulse noise, that means a good example of impulse noise is salt and pepper type of noise. we use what is known as a median filter, which comes under the heading of order statistics filter, which is an example for non-linear spatial filter. Okay, and instead of median, if I take the max value and replace it by the center pixel, or if I take the min value and replace it, I'll get actually max and min filters. Okay, so I think with this we will stop today.